She don't like her eggs all runny. She thinks crossing her legs is funny. She looks down her nose.
The focus of this video is on corollaries of Lagrange's theorem, and then some questions about the converse to Lagrange's theorem. So let's start with something about the order of elements in finite groups. Let G be a finite group and X an element of G. Then the order of the element X divides the order of G. And the proof is we're going to apply Lagrange's theorem to the cyclic subgroup generated by X. So Lagrange says that this order of the cyclic subgroup generated by X divides the order of G. But the order of the element X is the order of the cyclic subgroup generated by X. Okay, this next result I'm excited about because it's the beginning of classification results for groups of given order. So this corollary says, let P be a prime. Every group of order P is isomorphic to Z mod PZ. So what's going on here is we're specifying the size of the group and saying that every group of this size is isomorphic to this, or this, or this, or this. And when that size is a prime, that's the simplest that this can be. There's exactly one group of that order, and it's isomorphic to Z mod PZ. So we already know that every cyclic group of order n is isomorphic to Z mod NZ. So if we want to show that any group of order P is isomorphic to Z mod PZ, well, we already know that every cyclic group of order P is isomorphic to Z mod PZ. So we just need to show that any group of order P is cyclic. So let's suppose G is a group of order P. P is bigger than 1, which means there's some element in G that's not the identity element. Let's call that X. So because X is not the identity element, the cyclic subgroup generated by X contains at least 2 elements. So the order of X divides P by the previous results, and it's not 1. But the only positive integers that divide the prime P are 1 and P. So if the order is not 1, it must be P. So what does that mean? The cyclic subgroup generated by X has size P. So it has to be the whole group G. And that's it. So we've actually shown that if you take any element other than the identity, it's a generator for this group G. Okay, so sort of in this vein, I want to do one more of these classification type results. This one is actually an exercise earlier in the book before you know Lagrange's theorem, but it's a little easier now that we have Lagrange as a tool. So what I want to prove is that every group of order 4 is isomorphic to either Z mod 4Z, or it's isomorphic to Z mod 2Z cross Z mod 2Z. It's not hard to see that these two groups are not isomorphic to each other. The first one has an element of order 4, and the second one does not. All of the non-identity elements of Z mod 2Z cross Z mod 2Z, they all have order 2. So how do we prove this? We're just going to start with G being a group of order 4, and we're going to suppose that it's not cyclic. So that means it's not isomorphic to Z mod 4Z. So if we can show that it's isomorphic to Z mod 2Z cross Z mod 2Z, then we're done. Okay, so what do we know? This group G has 4 elements, 1, A, B, and C. And all we know is that 1 is the identity, and those other 3 elements are not equal to each other. So by Lagrange's theorem, what is the order of the element A? Well, it's not 1 because it's not the identity. And it's not 4 because G is not cyclic. So it has to be 2 because the only integers that divide 4 are 1, 2, and 4, the only positive integers. So if it's not 1 and it's not 4, it's 2. Same thing for B, same thing for C. All of these elements have order 2. So far, that property matches up with Z mod 2Z cross Z mod 2Z. So that's a good sign. So now what I claim is that A times B equals C. Why is that true? Well, what else could it be, right? If A times B was equal to 1, then B would be equal to A inverse. But we already know that A is equal to its own inverse because A squared is 1. So AB can't be 1. AB can't be A because then if you multiply by A inverse on the left, then B would have to be equal to the identity. and it's not. Same thing. AB can't be equal to B. So we have 4 possibilities because we know we have a group. We've eliminated 3, so it has to be the last one. AB equals C. BA, same reason exactly, it has to be equal to C. AC has to be equal to B. CA has to be equal to B. You can just write down what every product of elements has to be equal to. Okay, so now you've written down like the product of any 2 elements. And what I claim is that you can just define a map from G to Z mod 2Z cross Z mod 2Z that's a bijection by specifying where each of the 4 elements of G gets sent. And you can show that it's an isomorphism in like a totally brute force way by showing phi of G1 times phi of G2 equals phi of G1 plus phi of G2 for any G1 and G2. Here's one choice of map that will work. Send the identity to the identity. Send A to 1, 0, B to 0, 1, and C to 1, 1. There are many other choices that would work. And you can just check that this is an isomorphism. OK, so I don't want to do all of the details here, but hopefully the idea is clear that once you know that the order of every non-identity element is 2, because there's only 4 possibilities for the product of 2 elements, you can start to eliminate what those possibilities are to figure out what every product needs to be. OK, so let me pause and say we know every group of prime order is isomorphic to the cyclic group of that order. We know every group of order 4. So what are the smallest integers that are not 4 or prime? 6, 8, 9. And a little bit later on in the course, we will do the complete classification of groups of order 6, groups of order 8, groups of order 9. This is kind of interesting. We already know S3 is a non-abelian group of order 6. And we know 2 non-abelian groups of order 8, D8 and Q8. So we'll talk more about that later. For now, I'm going to pause and erase and give you one more kind of nice fact about special types of subgroups within a group. I want to prove a fact about a special kind of subgroup within a group G. So let's say that H is a subgroup of G of index 2. I claim that H is automatically a normal subgroup of G. And the idea of the proof is that one of the things that shows that a subgroup is normal is that if for each G, GH is equal to HG, that if left cosets are always equal to right cosets, then your group is a normal subgroup. So what are we going to do? So let's take an element that's in G, but not in H. So by assumption, what do we know about the left cosets of H and G? There are 2 of them, because it has index 2. So what are they? Well, there's the left coset of H containing 1, which is H. And then this element G is not in that coset because it's not an H. So the other one has to be GH because it has to be in some other coset, and there's one other choice exactly. So all the time when I'm talking about index, I'm saying it's the number of left cosets of H in G. But all of the definitions, everything that you do goes through exactly if you switch left cosets to right cosets. So you can think of a quotient group as being a group where the underlying set is the set of left cosets of K and G or the set of right cosets of K and G. So it's important to make a choice and then stick with it. But the number of left cosets and the number of right cosets are always the same. It's not true that the set of left cosets matches up with the set of right cosets, but the number of cosets is always the same. So there are also 2 right cosets. And for the same reason exactly, those are the right coset of H containing 1, and then the right coset of H containing G, because G is definitely not in the right coset of H containing 1, because G is not an H. OK. It is clear that the left coset of H containing 1 and the right coset of H containing 1 are equal because these are both h. These are both just equal to h. So this means we must have that the other two cosets are equal as well, that the left coset of h containing g is equal to the right coset of h containing g. So if you have an element in h, the left coset of h containing that element is the right coset of h containing that element, because that just is h. And if you have something that's not in h, we've shown that those have to match up too. So gh equals hg for all g in g. So h is normal in g. Okay, so later on in the course, we're going to see that this is a special case of a more general results about subgroups of index equal to a special thing in terms of the order of g. Okay, so I'm going to pause and erase. And now that we have this result at our disposal, I can show you a neat example. Let's think about the example of the quaternion group of order 8. So I've drawn the lattice of subgroups here. We've already seen that every proper subgroup of this group is cyclic. So we have the subgroup generated by I, the subgroup generated by k, the subgroup generated by j, the subgroup generated by k. These are 3 subgroups of order 4. Remember, each of these elements, the square is -1, and then -1 squared is 1. And we have the cyclic subgroup generated by -1, which is contained in each of these 3 and has order 2. Okay, what else have I drawn here is that these lines show the index of one subgroup in the larger group containing it. So subgroup generated by I has order 4, Q8 has order 8. The index of this order 4 thing in this order 8 thing is 2. So we have these 3 subgroups of index 2, and by the previous result, all of them are normal subgroups. Then we have this subgroup of order 2, and because it's in this, because it is the center of Q8, the center is always a normal subgroup. So what have we seen? Q8 is a non-abelian group, all of whose subgroups are normal. That's a weird property. There are other examples like this, and it's sort of like a nice group theory question, like how do you classify all of these non-abelian finite groups, all of whose subgroups are normal? So that's something that you can think about when you are presented with a new group. You can check sort of what kinds of properties does it have, like how do I write down all the subgroups? How do I understand which of these subgroups are normal? Things like that. So I'm going to pause and erase, and then I'll switch gears and talk about the last topic of this lecture, which is, are there converses to Lagrange's theorem that are true? One of the most direct consequences of Lagrange's theorem was this statement that if G is a finite group and X is an element of G, then the order of X divides the order of G. So we could ask, is the converse true? So what does that mean? If the order of G is equal to n and D divides n, does there have to exist an element X in G with order D? And the answer is no. If you think about the groups that we've already seen, you'll see that it's no pretty quickly. Just take D equal to n. So this would be saying G has order n. Does there exist an element X in G with order n? Well, that's exactly what it means for G to be cyclic. So the answer is yes if G is cyclic, and no otherwise. And we've already seen that there are groups like Z mod 2Z cross Z mod 2Z, which are not cyclic. Okay, a more interesting question is it true that if D divides n, then there has to be not an element of order D, but a subgroup, not necessarily cyclic, of order D? The answer here is also no, but it's a little harder to come up with an example. So we'll see soon in maybe 3 lectures after this one that there's an index 2 subgroup of the symmetric group Sn called An. So Sn has size n factorial, An has size n factorial over 2. AN is called the alternating group. So what does that mean? A4 has order 12. S4 has order 20. So A4 has order 12. And here I've just written down 12 permutations. You can check that this actually gives you a group. What are these 12 permutations? Well, it has to have the identity. And then it has 3 permutations that are products of 2 disjoint transpositions. Like 1, 2, and 3, 4 are transpositions. They only change 2 things. And they're disjoint, like the things moved by the first transposition and the things moved by the second transposition have no intersection. So 1, 2 times 3, 4, 1, 3 times 2, 4, 1, 4 times 2, 3. So that's 4 elements so far. There are 8 more elements that are 3 cycles. Like the permutation that takes 1 to 2 to 3, and then 3 back to 1. And 4 isn't written anywhere here. 4 is a cycle of size 1. It's fixed. So we know that we square this permutation, we get the 3 cycle 1, 3, 2. We have the 3 cycle 1, 3, 4. The square of it is the 3 cycle 1, 4, 3. 1, 2, 4, 1, 4, 2, 2, 3, 4, 2, 4, 3. So every one of these permutations that I just talked about cycles 3 things around and leaves the 4th one fixed. So, okay, so I'm claiming that this is a group. We'll see why pretty soon. And then I'm also claiming that it has no subgroup of order 6. So 6 is a number that divides 12, but there is no subgroup of A4 of order 6. So this sort of converse statement isn't true either. So I'm going to pause and erase, and then I'll tell you the closest things we have to converses to Lagrange's theorem. So the last thing I want to discuss in this lecture is what kinds of partial converses to Lagrange's theorem and its corollaries are true. So let's start with the one about orders of elements. We're going to prove a little bit later a big result called Cauchy's theorem. So let's say G is a finite group and P is a prime. From now on, I pretty much only want to use P to represent a prime number. So I'm not always going to say that P is a prime, but anytime you see P, you should think of it as a prime. So let's say G is a finite group and P is a prime number. If P divides the order of G, then there is an X in G with order P. So it's not true that if D is a number that divides the order of the group, that there always is an element X of order D, but it is true when D is a prime. If you have a prime dividing the order of the group, there exists an element with that prime order. What about this statement about subgroups? Well, the big result here that we're going to prove, again, later in the course, is called Sylow's theorem. If you have a group whose order is p to some power times m, where m is not divisible by p, then G contains a subgroup of order p to this power alpha. So G, the order is p to the alpha times m, where p does not divide m. So p to the alpha is the largest power of p dividing the order of G. There must exist a subgroup of order p to the alpha. So if you have a subgroup of this order, and Sylow's theorem says that you always have at least one, it's called a Sylow p subgroup. So one big thing that we're going to do later in the course is try to understand groups by understanding their set of Sylow p subgroups. So Cauchy's theorem is true for any finite group. Sylow's theorem is true for any finite group. If you restrict to groups that satisfy additional hypotheses, like being solvable, that we'll talk about soon, or super solvable, then stronger converses will hold.